Map your carbons. Oh, that's actually not number 1, but I did put it as number 1. No, maybe it is number 1. I mean, it doesn't really matter. Map your carbons. The last one I'm going to say is work forward and backwards. And the middle one, brainstorm. You looked that up?
Yeah, I used my Command F on my old notes.
Hey, that's a really useful part of typing your notes. Although I don't know how you do it, because this is such a visual class.
I type everything, but I'm like, oh, I need to remember that. And I go home and I write down everything I took photos of on the board.
Wow.
She almost gets you verbatim.
Crazy. All right, step 1, map your carbons. Step 2, brainstorm. And step 3, work forward and backwards. So I want to show you how that kind of applies here to that first synthesis that we completed last class. I'll be honest, mapping carbons doesn't really seem to do anything for me here. I can tell what's going on. This carbon, this tertiary carbon, is becoming a quaternary carbon. Okay, so it's not like I'm changing a lot about the structure. I'm not doing something intramolecular and having carbons attack other carbons. I'm not even really adding on a long carbon chain. I'm just adding 2 carbons. So if I wanted to map anything, I might say, look at this tertiary carbon becoming this quaternary carbon, and look at how I add 2 groups. You can always modify how you map it as you go. Mapping is really just a handhold, some way for you to kind of look forward and backwards. All right, as I brainstorm, I think about what functional groups I have and what functional groups I want. The functional group I have is alkane, and there is not a lot I can do with alkane. So in brainstorming, I'm definitely thinking about radical halogenation. Radical halogenation, I don't know why I stopped putting halogenation, but that's going to be Br2 and light, and that is a regioselective reaction. It will always place the new bromine at the most substituted carbon. Hey, conveniently, that's my starred carbon. So by mapping, I'm able to kind of use my brainstorming to validate what I'm thinking of. If I want to end up with an alkane, I'm going to need to do carbon-carbon bond formation. And there's a few ways that I've seen carbon-carbon bond formation. We reviewed this. We could have an acetylide group act as a nucleophile. Well, that does SN2, and if I put an alkyl halide here, I can't do SN2 on a tertiary carbon. So acetylide would give me 2 carbons, but I wouldn't be able to attack using the acetylide at that position. So one of my options here is the acetylide ion, but I can't do SN2 on a tertiary carbon. So I'm brainstorming it, crossing it out because it doesn't work. Then we also said I could have cyanide. Well, cyanide, same thing, can't do SN2 and doesn't even provide 2 carbons. And then we have our organometallics. Organometallics make carbon-carbon bonds. But again, I can't do SN2 on a tertiary carbon. So I'll need my organometallic to be on that starred carbon. That tertiary carbon will become my nucleophile. Okay, that then gives me a better idea in this brainstorming that I'm going to need an electrophile with carbons 1 and 2. And an electrophile is going to need a good leaving group, some halogen, most likely, coming off of it. Already, I'm kind of working forward and backwards. The first thing that I can do is radical halogenation, regioselective. The last thing that I want to do is I want to introduce an electrophile with carbons 1 and 2, where carbon 1 has a good leaving group. So if carbon 1 can be attacked, now I have a new bond. That means that my starred carbon has to be the reagent that attacks, has to be my nucleophile. This is how I work forward. I know what I can do with my starting material. This is how I work backwards. I know how I can get my final product. Now I meet in the middle. That's not hard to do. That's just the conversion of an alkyl halide into the Grignard. What reagent do I need there? Sorry? Magnesium. And did it have to be magnesium? No, I could have just as easily done lithium and created an organolithium instead of a Grignard intermediate. All right. So let's try and apply this for our next one. I've got, yeah, Peyton.
Sorry, just to clarify, I thought lithium was also considered a Grignard.
No, Grignard is the organomagnesium halide.
Okay.
That's why we don't name them after dead people, because it doesn't make sense what it is when it's just a guy's last name. The organomagnesium halide is, in essence, do you want that?
Yes.
Equally reactive to the organolithium. Either of these two groups will do the exact same function here. It's great. But they're not both Grignards, because Grignard implies having magnesium. It's kind of like Friedel-Crafts. We talked about Friedel-Crafts alkylation and Friedel-Crafts acylation. But if you use a different starting material, instead of an alkyl chloride, if you have an alkene that forms a carbocation, it's no longer Friedel-Crafts alkylation, it's just alkylation. Because Friedel-Crafts has the name, when it's an alkyl halide, as the reagent. Similarly here, it's lithium instead of magnesium, so it's not a Grignard because it's a different metal. Does that make sense?
Yeah.
So for you to think of them as being the same, that's good, but they're not communicated as with the same name. All right, for our second synthesis, we've got this 1, 2, 3, 4, 5, 6 carbon chain. And on one end is an alkene, and on the other end is a bromine. At the end, methoxycyclohexane. Should we map our carbons? Yeah, it's a good idea. Okay. So somehow I need to take these 6 carbons in a chain and I need to link them together. So I can start numbering wherever I'd want. I'll number from the left and I'll number to the right. Now I can't quite say where carbon 1 is and where carbon 6 is, but it should be obvious that at some point I'm going to need carbon 1 and carbon 6 to bond to each other. How do I make that carbon-carbon bond? That's part of my brainstorming. I'm going to need carbon-carbon bond formation. That should make me think to produce some sort of Grignard or organolithium. So I'm suspecting carbon 6 would be a great spot to make an organomagnesium halide.
Would it be possible, I was thinking maybe we could turn the alkene into an alkyne and then use amide to get like the anion and do like an attack or something?
Sure. So do a bromination here. So I have a vicinal dihalide, and then do a double elimination to make the alkyne, deprotonate the alkyne to attack the other side. I think the only issue there is when I start doing the elimination on the dihalide, what's going to stop this halide from also going through an elimination and forming an alkene? Right? I wouldn't actually be able to control the fact that this dihalide goes through elimination, but this halide doesn't. So that would work if I could control the reactivity of the eliminations. But I don't think I can control it. So I say instead, let's turn that group into our nucleophile. We'll turn the bromine on carbon 6 into a Grignard or into an organolithium, and we'll make carbon 6 the nucleophile. Well, then I just need to find a way to attack carbon 1. And I want to make sure I attack carbon 1 and not carbon 2. So if I could make a good leaving group on carbon 1, a good leaving group on carbon 1, then my nucleophile on 6 can attack carbon 1. What would be a good leaving group to put on carbon 1? A halogen would be a good group. An alcohol would be a bad group, because if I produce an alcohol there and then I make an organometallic, I don't do substitution, I just ruin my organometallic. Yeah? Then I can think about ways to control the reactivity of this group to place something on the least substituted carbon. Anti-Markovnikov alkene addition. HX with peroxide has regio control to the less substituted carbon, so my halogen will end up on carbon 1. But there is a problem here, which is if carbon 6 attacks carbon 1 and forms a ring, that just leaves me with cyclohexane. And it doesn't give me any way to make an ether group directly. Once I get back to an alkane, the only thing I can do is radical halogenation, and then I could do some sort of substitution. That's a plausible pathway. Make a Grignard, have it attack itself, and then just do radical halogenation and substitution. But there is another pathway that's plausible that might be shorter. Let's take the idea of using the alkene and the regio control of having a good leaving group here, but let's see if we can place the ether directly onto position 2. If 6 can attack 1, or to be honest, if 1 can attack 6, and I have an ether already on carbon 2, I'm killing 2 birds with 1 stone. So what would this need to look like beforehand? I would need to have, I'm going to draw this kind of already in the conformation that it's in. I would need to have a good leaving group on carbon 1, and I'd need to have a nucleophile on carbon 6. Although alternatively, because it doesn't really matter which one is the nucleophile, I could have a nucleophile on 6 and a good leaving group on carbon 1. I think I said that wrong. I could switch the position of where my nucleophile is. It wouldn't change the fact that one carbon attacks the other and completes the ring. So now I'm looking for a way for carbon 1 and carbon 2 to go through an alkene addition reaction such that a good leaving group is placed on the least substituted carbon and an ether is placed on the most substituted carbon. Ring any bells? You guys, Polar Express? Like all the adults are like, no, there's nothing in there. And the little kid's like, Santa Claus gave it to me. I think that's what's going on. You guys are trying to ring this bell, but halogen, ether from an alkene. What would you name that reaction? Halo ether addition. We learned it, didn't we? Rings a bell? I asked you to know the mechanism on the OCHEM 1 review. You should know the halohydrin addition mechanism and the haloether addition mechanism. So this is a reaction that we can actually think about. Now I'm going to put that in there. I'm going to have the haloether. And this is regioselective because water or alcohol will attack at the more substituted position, and the halogen will end up on the less substituted position. And that all has to do with charge stability when the nucleophile attacks. Okay, so here's my real question. If I can do haloether addition and place a halogen on the least substituted carbon and an ether on the more substituted carbon, does it matter when I form my nucleophile? Could I form my nucleophile now, put in magnesium and make a Grignard, and then start to do the haloether addition, Br2 with alcohol? Maybe, but the bromonium ring intermediate, when the bromine reacts here, that's an electrophilic intermediate, which we know likes to be attacked at the more substituted carbon because the ether will form on the more substituted carbon. The nucleophile attacks at the more substituted carbon. If I have a nucleophile in the form of an organometallic already, and I form the bromonium ring, that nucleophile will be the first to attack. Intramolecular reactions happen very quickly. All it takes is a conformational change. I don't have to wait for two molecules to find each other and run into each other. So, if I form my nucleophile and then add bromine, I will not get this product. I should first do the haloether addition. Br2, CH3OH. How do I know it's CH3OH? Because I want OCH3. Whatever my ether linkage is, I want that to be my alcohol carbon chain. I've got a methoxy ether, so I'm going to use methanol. Carbons 1, carbons 2. I have a good leaving group on carbon 1. I have an ether on carbon 2. And I have a good leaving group on carbon 6. So now when I add magnesium or lithium, because it doesn't really matter, I form one of those two intermediates. Can I control which bromine the magnesium will react with? Not really. But as long as one of them is turned into a Grignard, then the other acts as the leaving group. So it doesn't matter which attacks which in this case. And this never actually forms. As soon as this intermediate is generated, it reacts with itself, and this is the product that we see. This is a two-step synthesis. Haloether addition, SN2 by Grignard formation. How fun. Yeah. Your head's shaking the wrong way. It's like this. Oops. Okay. I realized after class last week, on Tuesday, that I didn't show you any of the mechanisms for the three reactions with organometallics, which were SN2, you've already seen those mechanisms, NAS, you've already seen those mechanisms, and acyl addition. You probably haven't seen those mechanisms. I'm not going to have you guys do mechanisms in this unit. Your written work has 2 synthesis problems and no mechanisms. So I'm going to show you the mechanisms because students in the past have asked for the mechanisms to understand what's happening here. But I want you to know that you're not being tested on these mechanisms. Okay? Should we go through them? Let's look at this mechanism. Let's say that I formed a halogen on carbon, or excuse me, a Grignard on carbon 6, and my halogen remained on carbon 1. What does the SN2 mechanism look like? How many steps in an SN2 mechanism? 1. Great job, Yvonne. Where's my nucleophile? Come on. This was a lot of our conversation Tuesday. Yes, the carbon next to the magnesium. And it's these electrons that carbon owns and will use in its nucleophilic attack. If you don't like how that looks, remember that this is essentially equivalent to this. Although I'm not sure why you'd like how that looks better. Those 2 electrons, those are essentially just a lone pair on carbon. And so, of course, that carbon is incredibly drawn to the partial positive on this other carbon. Magnets clicking together. That's it. That's my mechanistic step. And my byproduct is magnesium bromide, MgBr2, SN2, simple. In the NAS mechanism, let's show NAS with an organometallic, but let's have an electron withdrawing group on there so that we can see how the resonance is stabilized by the electron withdrawing group, because I don't know that I still did a great job demonstrating this for you guys. Methyl lithium. My nucleophile. The methyl carbon. Oh, you know what? We have an NAS one, but it's okay. I'd rather show you something like this. This carbon is nucleophilic in the same way that this carbon is nucleophilic. So methyl lithium, carbon takes the electrons and attacks the partial positive on the aryl chloride carbon. Well, that's going to push electrons towards the nitro group. Oxygen wants to take those extra electrons. Carbon doesn't. So this pi bond in the ring shifts over. The next pi bond in the ring shifts onto the nitrogen, CN double bond, and that forces open the NO double bond. Now oxygen holds the electrons. There are 3 other resonance forms of this intermediate. And you can draw any of them in any order because none of them exist. They all exist at the same time. But this is the one that is the most stable. This is the one that looks the most like what the structure's molecular orbitals actually look like. This intermediate forms along with its resonance forms. This is the major resonance form. And after this resonance form, my arrows shift back. Oxygen forms the NO double bond. CN double bond shifts back into the ring. Pi bond shifts over in the ring, and my leaving group leaves. I went from para-chloro-nitrobenzene to para-nitrotoluene. Milena.
This question on the other problem in which we first added the ether and then we closed the ring. I know you mentioned that we could have closed the ring first and then added the ether and the oxidation and all that. So how does Grignard interact with the double bond?
With the double bond itself, probably no interaction. Possibly, because I actually don't know the answer to this, it's possible that if we just added magnesium here, the Grignard may actually deprotonate one of the vinylic hydrogens. Why would that be favorable? Because sp2 carbons are more acidic than sp3 carbons. So an sp3 Grignard would be more basic than this sp2 carbon. That would just change the position of where your Grignard is now, where your nucleophilic carbon is. It certainly would complicate the synthesis. I did skip over that other solution though, and I do want to lay out that solution. The other possible solution that we had was adding HBr with peroxide, which gives this dihalide intermediate, but no ether, yeah? And now if I add magnesium, I essentially do what we did up here. I just have SN2 on a carbon to carbon, but this time it's intramolecular, forms a ring, and leaves no functionality other than alkane. And this is where I would have to further do bromine and light to get some reactivity there. And then I could do substitution with an alcohol. It's more steps. And generally, I don't take points off if your synthesis is more steps than it needs to be. But I have definitely worked with instructors that grade by efficiency, do a synthesis in the least number of steps possible. I think if that's going to be the assessment criteria, then I need to do a very good job of explaining to you how to be efficient. I have a hard enough time getting synthesis in. So if you can solve a synthesis, that's great. Efficiently or less efficiently. Okay, the other synthesis, okay, I guess I'm kind of wrapping myself in knots because I also wanted to show you acyl addition, a mechanism for acyl addition. If you guys recall, acyl addition had two steps over the arrow. It had first an organometallic step and second an acid workup step. This is another reason why I don't like to give you these mechanisms, because when showing a mechanism, there's no good place to say this step ends and this step begins. It's a little cumbersome. So I don't typically have you show mechanisms for something like this. But it's an easy process to show. Let's say that we have acetone and N-butyle. By the way, did I tell you guys why it's called N-butyle? Instead of just like butyle? What's the N trying to describe? It's that the lithium is attached to a normal butane chain, a straight line. There's also sec-buly, isobuly, tert-buly, or S-buly, T-buly. My nucleophile, again, is that carbon to metal bond. And this time, my nucleophile attacks at the partial positive of the carbonyl carbon and breaks the pi bond open to oxygen. So that leaves an intermediate for me. In this case, it would be OLI. Covalent bond? No. Ionic bond. So if you don't want to show that as OLI, just to neutralize the charges, you can show those charges separately, O minus and Li. Do you remember what the product of acyl addition is meant to be? What functional group do we acquire? Start with a carbonyl, and that's why we call it acyl addition, and produce, not a carbonyl. Produce what?
An alkyl carbon?
Produce an alcohol. It will be an alkyl carbon, you're right. It'll now be sp3 instead of sp2. The oxygen stays attached. Is that an alcohol? That's an alkoxide. That's an anion, certainly not an alcohol. So how do I get an alcohol after acyl addition? A second step, an aqueous workup. Those of you that were in lab, you did this. You made a Grignard, you attacked a ketone, and then you stored it for the week. And you left it as that anion. And then you came back the next week and you added acid to it and you worked it up to make it an alcohol. That's the aqueous workup. How do we show that? We show H+, or we show the acid, H3O+, and here's my acid-base reaction. Oxygen takes the alcohol, oxygen takes the hydrogen and becomes an alcohol. I can ignore some of those waste byproducts like the lithium and any of the water. I don't know what happened with Zoom. Ozzy and Lily both left. Yeah, Max.
I just have a question, because in the last reaction, the lithium, the negative side of reacted to from a ring. So I'm guessing is that it goes towards more the partial positive, which is going to be that group because of the electronegativity of the oxygen.
Good.
But what do we have a cyclopentane byproduct in this case?
No. Okay, so we have to consider whether it's intermolecular or intramolecular. The only way that we could make a cyclopentane is if I had one part of the molecule attacking another part, like we see up here. One part of the molecule attacks another part. One part of the molecule attacks another part. I'd have to have both nucleophilic character and electrophilic character on the same molecule. Actually, this is there's a cool application here in cancer-causing chemicals, methylating agents, is that they have a nucleophilic component and an electrophilic component within one compound. And they can form rings through intramolecular reactions. Here, I have a reagent that is nucleophilic and a reagent that is electrophilic, but no reagent that is both nucleophilic and electrophilic. So I can't have one reagent attack itself. N-buly has only the partial negative. It has nowhere to attack a partial positive on any other neighboring N-bulys. And acetone, it does have partial negative and partial positive, yes, but it's unlikely that it polymerizes. One oxygen will not attack the carbon of a neighboring group. It's just not favorable. Yeah. But get them both together, I now have a good nucleophile and a good electrophile, and I have an intermolecular reaction. If we map our carbons, Remember, I like to count through my nucleophilic attacks when I can, because that's how my carbon chain is going to expand. So 1, 2, 3, 4. 4 attacks 5. 5 has a methyl group and is bonded to 6. 1, 2, 3, 4. Oh, it's too short. Is that what you were maybe pointing out?
Oh, no, I was not pointing that out.
That structure is wrong. Oh, good thing I mapped my carbons, huh? Why is it wrong? Because the oxygen is bonded to carbon 5, not carbon 4. And carbon 5 has a methyl group and 6. Carbon 4 doesn't have a methyl group. Okay, so here's what I'm going to do. Boop. Just add another carbon on this end and push these carbons down to the left. 1, 2, 3, 4. 4 attacks 5. 5 has a methyl group, and 5 is bonded to 6. Even this intermediate only has a negative charge. It doesn't have anywhere else to attack, so there won't be any cyclic formation. Does that make sense? Mm-hmm. Answers your question of why we don't get a cyclopentane?
Yeah.
Good. Great question. All right, let's look back at the last synthesis. As I copy it onto the board, I want you guys to think about brainstorming what reactions are going to be included in this. Map your carbons. Where do the carbons start? Where do the carbons end? Do I lose any carbons? I made this last year, and I can't tell if I made a mistake in my carbon chain or if I was expecting something longer in my synthesis. Sorry. Did you map your carbons? It's obvious to tell where the ring is, right? Let's call that carbon 1, where it's connected to the alkyne group. And then we can pretty easily refer to these other two as 2 and 3. Although, because we see the ortho carbon is also involved, maybe it's better to call this 1 at the top and come down to 2, 3, and 4. Now I've got 1, 2, 3, and 4. Who's that? Carbon 5 is going to have to come from somewhere. I'll have to add a carbon at some point in this process. There's a lot of ways to do that. In fact, that means I need to form 2 carbon-carbon bonds. I need to form a bond between 4 and 5, and I need to form a bond between 1 and 5. So I'll need to form 2 carbon-carbon bonds here. Who brought up earlier the idea of making the alkyne here into a nucleophile and adding 1 extra carbon? Great idea. Let's brainstorm that. Acetylide. Oops. If I make an acetylide ion, it could attack an electrophile. What would I want that electrophile to look like? A methyl group. I could have it attack methyl bromide, methyl iodide. I'm going to show you methyl iodide because I don't want you guys to forget that there are other halogens out there. If carbon 4 becomes a nucleophile, it can attack carbon 5 being this methyl iodide group. Great. But what about then the idea of 1 connecting to 5? How am I going to do that?
Would it be possible to have 2 halogens in that methyl, or would that complicate things?
It might complicate things to have a CH2X2, but it would be useful because what you're saying is I can substitute 1 here, and then I have a second one to substitute here. Good. I'm trying to think if there's another way for us to do it, and there is. There is another way for us to get a halogen there, but it adds extra steps. I'm going to show that way because I think it would be easier. But if you track what Milena's saying, you could have CH2I2, diiodomethane, and now you're set up for a second substitution. Here's what I'm going to show. At some point, I'm going to have to reduce the alkyne. Do you agree? That alkyne has to become an alkene. How do I do that? Well, I could do HCl, but if I do HCl, it'd have to be anti-Markovnikov because I want the H to add where there are less H's. So it'd have to be HCl and peroxide. I think I erased it, but I had something similar before. But I'm already thinking about adding another carbon there. So it might not be good to put a halogen on that carbon.
I can't remember what the solvent's called, but could you do like the NH3 and take the hydrogen off and then put like a CH3 group?
Yes, actually that's what we'll do here. NaNH2 and then add a CH3 group. But then to turn the alkyne into an alkene, I can do Lindlar's catalyst, or I can do sodium in ammonia. But those have very different effects on the stereochemistry. Sodium in ammonia gives a trans alkene. Lindlar's catalyst gives a cis alkene. And I need it to be cis for this structure. If I get down to a cis alkene, then I could actually do allylic halogenation. I can place a halogen on the allylic carbon by doing radical halogenation of an alkene. But I still need something that can attack that position, or I need that position to be able to attack the ring. So I need a good leaving group on carbon 1. How do I do that? Halogenation of the ring, Br2, FeBr3, bromination of the ring. Now I have a good leaving group on the ring that I can attack. It's complicated, huh? It looks like this is going to be a lot of steps already. So let's solve it out. Again, there's oftentimes more than one right way, more than one plausible way to do this. The order can be a little bit ambiguous. So let's start by doing NaNH2, which deprotonates the alkyne and makes it into an acetylide ion. And then let's add our methyl iodide. Now that we've done that, let's reduce our alkene into our alkyne into an alkene. Which gives a cis alkene. From here, I could do either of my halogenations in either order. I'm just going to stay with what we discussed as we were brainstorming. I'll do my allylic halogenation first. Then I'll do my aryl halogenation. Can I be confident that the bromine is going to go to that position I need it to go to? That it will go to carbon 1? How do I know it won't go to a meta position or a para position? Well, actually, I can be confident it will go either ortho or para. And remember that I told you earlier with EAS reactions, if it is possible to go ortho or para, then ignore the structural isomer that you don't want. It could have gone para to my alkyl group, but it can go ortho, and that's the structural isomer that I will isolate and work up, which is a pain. That's the job of an organic chemist. It's painful. Now what? Much like last time, that first reaction, I've got two groups that could become the nucleophile or stay the electrophile, and it wouldn't matter. And as soon as I add the metal, one of them becomes the nucleophile and immediately attacks the other. So I won't even see the intermediate. I won't know which carbon attacked which. As soon as I add magnesium here, the reaction's done, I've got my product. That is a really challenging one. Trust me, that's not what you'll see on the unit test or on the exam. But it provides some very good thought process for you to go through. Did that sheet only have that on it? Great, love that. Ask any question you got.
I thought that CO2 and heat
Oh.
That's
That's actually not heat,
oh, light.
light.
I thought it was only on like sp3 hybridized.
Ah, you're right. And that is an sp3 hybridized carbon.
Oh, I'm so dumb. Okay, never mind.
No, that was
I'm in a different world.
actually, that was not a dumb question. That was a great question. It was exactly right. And that's a good reminder about being able to identify allylic positions. Here's the alkene. This position attached to it is the allylic position.
My mind, I was like, that one, I don't know. There was no, I skipped a step, yeah.
All right, now if you're really thinking about your allylic radical halogenation, you might remember that I said we often get these 1,3 allylic isomers. So this also has a structural isomer that forms that looks like this. But which one is more likely to form? Which one would be more stable?
The one we're using,
Why?
because it's sp2 in the reduced position.
Good. The one that we formed has a conjugated alkene. It's conjugated to the ring. That's a good thing. This alkene is not conjugated to the ring. Not as good. On the other hand, the radical that this forms from is more substituted and conjugated to the alkene, which means this radical is more stable. And this radical is less substituted and not conjugated to the alkene and is less stable. So we actually start to see some kinetic and thermodynamic differences here. Di-substituted alkene, more stable. Conjugated to the ring, more stable. Monosubstituted, not conjugated, less stable. So again, two possible structures. If I got both in a lab, I'd have to work them up. Come in at 8 a.m., set up a giant column, pour in some solvents, take them all out, look at their TLC plates to see where my compound is, isolate the compound I want, go home and cry. Questions on the mechanisms or on the synthesis that I can answer? Yeah. I know that feeling. She just said. Should we take our break? Or do you guys want to get into preparation of alcohols? 5-minute break? Okay. Let's come back in at 6 and pick up with how to make alcohols. I was like, hey, I think that's mine.
And I just looked at the ones that I submitted and I was like, hey girl.
You did great. So my 2 Zoom students left. Should I just close it?
Yeah.
I don't know if it was the...
They send you a message or anything?
They didn't, no.
So it wasn't like connection lost or anything?
Well, I don't know because Lily came in and then she left and then she came back in. And then Ozzy came in and then Ozzy left. So I don't know if maybe my audio is broken. They're not hearing me. I didn't get any messages, I don't think. Like they didn't put anything in the chat.
What about an email?
No email. So I don't know what happened. We'll have to find out. Maybe it could be they couldn't hear me well and they could hardly see the board and they were just like, never mind, it's not worth it. It's hard to know how to do this well, you know? Back in the day, it was just show up or don't show up. And then COVID happened, and I was like, oh, you can really just record everything.
It's so nice. I love that. It's so helpful.
Have you guys been on Canvas today?
No.
Are my...
Not your Canvas.
Does the homepage look different?
No, it looked the same earlier today.
I'm finding that my things are like not on the same line that they used to be. Oh, okay. Yeah, like they used to be, like it would be the dot for unit 1 and then on the same line as that, the icon for unit 1 and then on the same line as that, the link to unit 1. But then I was looking at it right now and it's like not showing up in line. That looks better. Mine are showing up offset. How bizarre. That looks great. That's exactly what I want it to look like.
Genuinely so shocked. Why did you I have no idea. I genuinely have no idea. Like, I'm actually very shocked. Because
felt good about it. I was like, oh, isn't that always the best? I literally had to go. That's always the best one. It was so good. Like,
I didn't think it was like good, but I was like, I at least got like, I at least got like a minimum, like an 85.
Did anybody need this sheet for preparation of alcohols?
oh, actually, yes. Wait, yeah.
It's on the back of preparing organometallics.
It is?
Okay. Yeah. If you've got your organometallics, you've got this one. Oh, that's okay. Well, they're going to sit in my office otherwise, so wouldn't say it's you wasting them. Is that what I made? Is that the right number? Yeah. Let's do a review. A review of the review that we've already reviewed. How many different ways can we make alcohols? If you have your notes from earlier in the semester where we reviewed reactions, now would be a good time to pull it up. Huh? Yes, James, you're right. We're not looking at making whiskey tonight. Maybe after legislation loosens the law a little bit, we can have a class on how to distill your own alcohol. But at the moment, it's illegal to distill your own alcohol. And sell it, I think. I don't know.
But is it just in Utah? Or is it
Yeah, other states have looser laws on that.
educational purposes?
Well, actually, we used to have a lab where we fermented sugar with yeast, and we distilled the ethanol that was produced. And we tried to distill it as purely as possible. Some of the instructors were like, I'm pretty sure this goes against the law. And I was like, I'm pretty sure the law is about drinking alcohol, and this is not something you can put in your mouth. Why? Because it's in a chemistry lab. Don't put anything in your mouth. So I don't think it broke the law. I stand by that. And if a legislature wants to come down and tell me I broke the law, then I'd tell him, put it in your mouth. And you'll fail my class. I'll kick you out. So anyways, how do we prepare alcohols to the functional group? Acid catalyzed hydration, H2O, H3O plus. What structure do I get from this starting material? 2-methyl, 2-butanol. Do you remember the key feature about this reaction? About the mechanism? It forms an intermediate. What type? Carbocation. Carbocations will form at the most stable position of the alkene, which is, of course, the most substituted. In this structure, that allows for a carbocation rearrangement before the alcohol actually forms from the water adding. That's why I like this little alkene, because it reminds us of carbocation rearrangements. What else? Me.
It's because I wasn't here on Tuesday, so I was watching and I didn't finish watching.
That's good. That's good. Acid catalyzed hydration. Oh, well, give me the chemical formulas. I know what they are. Oxymercuration, reduction. Mercury acetate and water, followed by a reducing agent, NaBH4. This is a Markovnikov addition, but it avoids carbocation rearrangements.
Is Markovnikov
It depends on how you like to think of it. And I've actually had people say they like to think of it different ways. So Markovnikov is H adds to the carbon with more H. So the hydrogen adds to the less substituted. The way to think about that is that the new group, in this case the alcohol, adds to the carbon that is more substituted. So some people like to think of how H adds, Markovnikov is less. Some people like to think of how the other group adds, OH is more.
Sorry, I just can't read. After HG it says
OAC.
OAC. Okay, I thought you said argon.
OAC is actually this. And we abbreviate it as OAC. And it's subscript 2. We've got 2 acetates bonded to our mercury ion. Yep. Okay, what else? Hydroboration, oxidation. Step 1, BH3. Step 2, basic, aqueous, hydrogen peroxide. H2O, H2O2, and NaOH. If it's not basic, it doesn't work well. If it's not aqueous, then it's very concentrated and it could overreact. And the benefit of this formation of alcohols? Anti-Markovnikov. Great. Okay, those are our 3 hard hitters from alkene addition. Couple of others that we should remember. Halohydrin addition. Let's say Cl2 and H2O. This is very similar to the halo ether, but instead of using an alcohol solvent, I use water as a solvent. Water is a precursor to alcohol. Alcohol is a precursor to ether. All right. My alkene addition can also give me diols. Osmium tetroxide or cold potassium permanganate. This is a syn diol addition. I'm not focusing on the chirality or the stereochemistry here because it's just not one of our main focuses in this unit or this chapter. Well, here's a good question. How many of these 5 so far are chiral? How many products shown are chiral? 3? 3? Chiral? No, every carbon has at least 2 identical groups. Chiral? Yeah, the alcohol carbon has 4 distinct groups. Chiral? No, every carbon has at least 2 distinct groups. Chiral? It's the alcohol carbon again. Chiral? The secondary alcohol carbon is chiral. The primary alcohol carbon is achiral. Okay. Sorry, that's it. I don't have another alkene addition reaction, so that last guy is empty.
Is the alkene still there, or does it disappear?
From here to here?
Yeah.
Yeah, these are all alkene addition. An addition is using the pi bond to add 2 new groups. No alcohols.
It looks weird because the OH is so far away from the alkene. It's just.
Yes, it is. It is. So here's how that happens, Max. In acid, the alkene is a base. So the alkene takes the hydrogen from H3O+, which leaves in its wake a carbocation. But that carbocation is not as stable as it would be on the adjacent carbon. So a simple methyl shift, a simple hydride shift leaves a new carbocation in its wake. And this is what water attacks and bonds to. And that is what I want. That's why I have this alkene as the example. It's to show how crazy it is that the alcohol adds to a carbon that was not a part of the alkene because of the nature of that carbocation rearrangement. Okay, but there were a couple of other ways that we've already seen ways to make alcohols. By the way, I keep forgetting to say this, but these are all previously seen. One of our other previously seen reactions, can you guys think of it? A way to make an alcohol. Substitution. And what did you say? Substitution to make an alcohol. So we can see SN1. I can use something like water on a more substituted carbon, and I make an alcohol. I can see SN2 if I have a less substituted alkyl halide. I can use a strong base like hydroxide. And then there was a new form of substitution we learned this semester that can also make alcohols, NAS. And we can also call NAS SNAR. Because it's not first order nucleophilic substitution, it's not second order. It is second order. But it's not the second order that was called the second order nucleophilic. Have I told you this? I hate the name SN1 and SN2. It's terrible. It presumes to be the only first order nucleophilic substitution and the only second order nucleophilic substitution, and it's not. SNAR is also second order, but it's unique to being an aromatic ring, so it's different. Okay. In this NAS, we need an aryl halogen, and we need a strong nucleophile. This cannot be water. Water will not do it. Hydroxide can substitute. Now, this is just an example. Could you change anything to that benzene ring and allow this reaction to occur more quickly? Indigo?
Would you try adding a group of either forced to be para or kind of like the sugar one, like over powder? Would that make it faster or just?
Should I add an electron withdrawing group or should I add a donating group? A withdrawing group. I already want a positive charge on the carbon to draw in that negatively charged nucleophile. So if I add another group that pulls electrons towards itself, and like you said, Indigo, if that other group is ortho or para, it will speed it up. But it needs to be a group that withdraws electrons. Electron withdrawing, ortho or para really speeds up this reaction. Great. Okay, and that is all the ways that we've already seen. I want to remind you that on Canvas, at the top of our module, I've got learning objectives, and all of these reactions are listed. So you don't have to just rely on your notes. You can actually go through that learning objectives document and make sure you've got all of those reactions down. Now let's look at new ways to make alcohols. You can see that I've given you this chart with a lot of different carbonyl groups. How many? 1, 2, 3, 4, 5, and then a 6. Can you name those carbonyl groups? I think we don't have enough for everybody, but we've got enough that every one can be named by a different person. Who's got the top functional group? Max? Good. Carboxylic acid. Who's got the second one? Andy. Esther. Good job. Who's got the third one? James? Aldehyde. What's missing from that aldehyde? The H. How about the fourth one? You can't take two, Andy. Yes, it's our acid chloride. Where have we seen the acid chloride before? Yeah, acylation. We can't say AlCl3 because that was used for chlorination, alkylation, acylation. But you're right. In our acylation reaction, we use the acid chloride. What's the one beneath it? Acid anhydride. And where have we seen that already? Also on the acylation reaction. We can use Friedel-Crafts acylation with acid chloride, or we can just use acylation with the anhydride. And then what's on the bottom, Yvonne? Ketone. Okay, got to know those functional groups. Good practice. All of the reagents on the top form the exact same product. That's what I'm trying to depict with this flow chart. They all use the same reagent, and actually it's 2 steps. First, LAH. Second, H3O+. I'm going to tell you what LAH is. That's lithium aluminum hydride. LiAlH4 Li plus AlH4 minus. Do you know who owns the electrons in a bond between aluminum and hydrogen? Do you know who's more electronegative? Hydrogen is more electronegative. This is a strong reducing agent. We talked about this a little bit last class. Reduction is what in terms of electrons? Gain or loss? Reduction is gain, oil rig. So a reducing agent is something that will give electrons to help a compound become reduced. It will give electrons to a new compound, the reducing agent. Where do those electrons come from? The H minus. H minus takes electrons with it to a new group. What group? What is H minus giving electrons to? Consistently across all of these compounds. No. The carbon. The oxygen is actually not being reduced or oxidized. The oxygen has 2 bonds to something less electronegative than it, and it ends with 2 bonds to something less electronegative than it. Oxygen is not reduced or oxidized. But the carbon, in each of these cases, loses 1 bond at least. 1 bond to an oxygen and gains 1 bond to a hydrogen, which means that it is gaining electrons by being bonded to more carbons. Carbon is being reduced. And the H3O+, what's this? Just like with our acyl addition, this is an acid workup. It just allows us to protonate everything after the basic reducing step. All right. I do want to point out that some of these products have extra byproducts. Sorry, some of these reactions have extra byproducts. When carboxylic acid is reduced to an alcohol, by the way, what's the substitution of that alcohol? Methyl, primary, secondary, tertiary, quaternary alcohol? Primary alcohol? How do we know? The alcohol carbon is bonded to one other carbon, which actually is consistent all the way throughout these compounds. This carbon bonded to oxygen is a primary carbon. It's only ever bonded to just one other carbon. When carboxylic acid is reduced, it forms an alcohol plus water as a byproduct. When the ester is reduced, it forms this alcohol plus a second alcohol. And I want to point out that it's the OR that goes on to become the ROH of this second alcohol. Just how carboxylic acid makes H2O, the ester makes ROH. The aldehyde has no other byproduct. This is exactly what forms, the only thing that forms. The acid chloride forms HCl as a byproduct. And the acid anhydride, well, it actually forms two equivalences of the alcohol, and it's because it at first forms a second carboxylic acid, which we know gets reduced to an alcohol. So I just formed two equivalences, one from each side. The ketone down here is reacting in the same way. First LAH, second H3O plus. Why is it the ketone forms a secondary alcohol instead of a primary alcohol? It's already connected to two groups. It keeps those two groups. So I want to phrase it like this. Carboxylic acid has a leaving group. Water leaves. Ester has a leaving group. The carbonyl carbon kicks off a group. The aldehyde does not have a leaving group. Acid chloride, chlorine acts as a leaving group. The acid anhydride actually has a leaving group that forms a compound that can also be reduced. The ketone has no leaving group. Carbons are not leaving groups. They don't fall off during this process. So all of our carbonyls form primary alcohols except ketones, which form secondary alcohols, because ketones are secondary carbons already. Once again, I am not asking you to know mechanisms for this, but in case you're interested, hydrogen acts as the nucleophile here. Hydrogen takes the electrons and attacks that partial positive carbonyl carbon. This is acyl addition. Absolutely. But we don't call it acyl addition as often, we just call it reduction. And that new intermediate has a negatively charged oxygen, and it's got this new hydrogen attached. Depending on what Y is, if this is my carboxylic acid, if this is my ester, if this is my anhydride, my acid chloride, sometimes Y falls off. And it leaves me with, well, would you look at that? An aldehyde. which goes through the same process. Another hydrogen attacks it. And now it has no leaving groups. Some of these are going through a double reduction. Is that fair? Carboxylic acid, ester, acid chloride, and hydride, they're going through a 2-electron reduction. They're getting 2 hydrogens added to them. Aldehyde and ketone, those are going through just a 1-step reduction. Okay. And this is what we'll call them. Reduction of carbonyls. As a means of preparing alcohols. As we move to the second box, the second set of things, what do we notice? There's a couple of functional groups that no longer react. This is what NR is telling us. We're going to be using, again, the same reagent here across all of these different functional groups to see what they give us. This time, we're going to use a different reducing agent. Instead of lithium aluminum hydride, we're going to use our old friend, sodium borohydride. And in each case, we'll follow it up with an aqueous workup. So I have a question. Why can aluminum hydride reduce everything it runs into contact with, but borohydride can't? Borohydride doesn't react with the carboxylic acid. Sodium borohydride doesn't react with the ester. We call this a moderate reducing agent. Because of its inability to reduce some of those carbonyls. So why can hydrogen take electrons from aluminum and attack everything, but why can't hydrogen take electrons from boron to attack everything? Between what? How does it compare to the electronegativity of hydrogen to aluminum? Hydrogen to boron has a greater difference in electronegativity? Is that what you're saying?
Yeah.
Greater difference in electronegativity, smaller difference? Smaller difference in electronegativity, less control over the electrons. Larger difference in electronegativity, more control on the electrons. Boron and aluminum are in the same family, which is why they form complexes that are similar to each other. But boron is higher up, and in a family, electronegativity increases up. So boron is more electronegative than aluminum. It's harder for hydrogen to use those electrons. Hydrogen owns the electrons better when it's from aluminum. It's less reactive when it tries to steal them from boron. Do you know what the difference is between aluminum or boron and hydrogen's electronegativity? 0.1. The difference in electronegativity here is 0.1. They're basically the same. They're closer than carbon and hydrogen are in terms of electronegativity. And yet we credit a bunch of stuff to this difference in electronegativity, and we pretend like carbon and hydrogen don't have any difference. Okay, anyways, aldehyde and acid chloride, NaBH4, followed by an aqueous workup. These form the exact same thing. They both form the same alcohol, the same primary alcohol, but the acid chloride also forms a byproduct of HCl. Actually, if you recall this example, let's say that Y is chlorine. When the acid chloride gets reduced, it forms this intermediate where chlorine wants to get kicked off. When chlorine gets kicked off and a carbonyl reforms, that's just an aldehyde. And aldehydes can be reduced by sodium borohydride. So when the acid chloride forms an aldehyde, the aldehyde gets reduced. It's a two-step reduction, just like last time. One hydrogen gets added, and then a second hydrogen gets added. But what about the acid chloride? I'm sorry, the acid anhydride. When I react with NaBH4, do you remember how earlier we said the acid anhydride produces a carboxylic acid? Right, so now let's say that Y is this oxygen bonded to another carbonyl group. When Y gets kicked off, that forms a carboxylic acid group. And carboxylic acids are not reactive to sodium borohydride. So the acid chloride gives me one equivalence of the alcohol that I'm expecting and one equivalence of a carboxylic acid, because the carboxylic acid won't be reduced. And the ketone, still reactive, still secondary, still forms a secondary ketone, a secondary alcohol. Looks just like this second step. Hydrogen attacks, but there's no good leaving group. How fun is that? You're right. Oh, you know what? I forgot. This is, again, all reduction of carbonyls. These are our new reactions, but there actually was one other way to make an alcohol that we did see already, and I forgot to put it in the previously seen section. We just talked about it, right? Acyl addition with organometallics opens up the carbonyl into an alcohol. I'm going to call this R1, R2, and now if I introduce R3, MgX, or R3Li, followed by an aqueous workup. Then I can take this carbonyl and I can add a third carbon group to it, make an alcohol. Yeah. There's one more I want to put on there. It's very similar to that acyl addition with the organometallic. The only change here is that we'll use cyanide. First, Cn minus, followed by an aqueous workup. We call this a cyanohydrin. It's a geminal alcohol nitrile. They're attached to the same carbon. Those are our ways of making alcohols. Congratulations. Now I have the next worksheet, which is ways to react with alcohols. And we also have some things on ethers and epoxides. One thing that I really want to do, though, is get to the synthesis at the bottom. So I think before we fill out this flow chart on the top, where we have an alcohol starting material and we'll show ways to react with alcohols, I want to look at the bottom down there. Thank you, Yvonne. My eyes don't work. Okay, you guys got all this? You need some time? I don't want to be that guy that erases stuff too early. We good? All right, so let's look down at the bottom of that sheet where we've got a bicyclic structure, a cyclic ether, and a ketone. We're going to do two things to it. One, we're going to react it with a reagent that reduces the ketone, but not the ether. Ester, excuse me. Two, we're going to predict the product of reduction with LAH. Let's start by filling in the reagent going to the right. I don't want to give this to you. I want you to convince each other. So don't tell me. Whoever feels the most confident needs to win the trust of everybody else in the room on what reagent takes us from left to right. What's different from this and this? Okay. But I mean, in terms of reagent, that's the same reagent, isn't it? Yeah. So I agree this would do this. But then wouldn't it also do this? Because it's the same reagent. At least she's honest. Max, are you convinced? You want to check with Milena and see if she's convinced in the same way, or convince her?
Well, what she said made sense, but that didn't answer my question.
Yvonne and Sarah, are you guys convinced now? You want to convince James and Indigo behind you? Milena, you and Max agree? No, you're fine. It's my brain. It's not you. I I think you guys are starting to be able to tell the difference between my new worksheets and my old worksheets. I'm using headers, and my old worksheets have no headers.
Your old worksheets are just vibes.
They're just vibes, and they're not helpful. Okay, who wants to lead the way on this? I think there might be only 2 people that aren't convinced. Is that true? Are you convinced?
I think Annie's so smart.
Do you want to convince Ella?
Do I want to convince you?
Ella.
Oh, no one's convinced. Yeah, sorry. I had to be convinced.
Good, that was the goal. You guys ever played in a tournament of rock, paper, scissors?
Yeah.
Where whoever wins now takes that team behind them, and they like, as you win groups, you like just keep going and
In a circle, right?
yeah.
Yeah, yeah.
And that's kind of like what I envision happening here is like whoever can convince the most people like wins the crowd and leads the way. But you guys kind of won in these pockets, so.
Yeah, well, it doesn't help that we all sit like way far away from each other.
It's true, it's true. Who wants to lead the way on this one? Max?
But I'll say it's just the NABH4 and the H3 plus reaction.
Good. Now, could I write that, Max, like this?
You need to do the 1 and 2, right?
Good. I need to have the 1 and 2. Why? Why am I going to take your points off if you don't put 1 and 2? Correct. If I tell you to go to the kitchen and scoop peanut butter and jelly, you might just take peanut butter into the jelly and scoop them both at once. Is that really what you meant? Or did you mean the peanut butter and then with a fresh utensil, the jelly? If you tell me sodium borohydride and H3O+, they kill each other. They don't exist together. I need first NABH4, then I can add the H3O+. It takes time. And you guys know what that's like because you've done things like that in lab. You run things for an hour doing a reaction, and then later you add in the next reagent. So Ella, are you convinced on this one now too? If I used LAH, I would reduce both carbonyls. LAH is a reducing agent for both carbonyls. NABH4 can be thought of as a selective reducing agent. That's what we're doing here, selective reduction. Later in the semester, we'll actually talk about why the esters and carboxylic acids are less reactive. All right, so that means if I use LAH, I should see both be reduced. What does a ketone form when it's reduced? Not quite. Give me more detail. A secondary alcohol, not just an alcohol, secondary alcohol. What does an ester give me when it's reduced? Primary alcohol and a second ROH, a second alcohol, which is going to be which carbon? Let's number my carbons counterclockwise from the carbonyl over to the ester linkage. What's going to be my R of that extra ROH group? Carbon 1 or carbon 5? Carbon 5. This is the ROH that will form. This is the primary alcohol. This is what we always expect. The carbonyl carbon always forms a primary alcohol. The ester linkage can be totally variable because this doesn't need to be a primary carbon. I could add a methyl group coming off of 5. I could add 2 methyl groups coming off of 5. I could have rings coming off. I could change what's going on at this position a lot, but whatever is at that position just becomes an alcohol. So I like to call this a primary alcohol plus a variable alcohol. Could be methyl, primary, secondary, it's no way to know. So as I have mapped them and now I try to predict them, I know that the ring on the left stays entirely intact the way it is, and the ketone becomes a secondary alcohol. But then I have position 1, 2, 3, 4, and 5. 1 becomes a primary alcohol, and 5 now also becomes a primary alcohol, my variable alcohol. I just split open a ring. I took a cyclic ester and I reduced it into a diol. And by doing that, the ring opened up. That doesn't always happen when you reduce an ester. I want to give you another example of reducing an ester. This is methyl acetate. When methyl acetate is reduced by LAH, because that's the strong enough oxidizer for it, I make both ethanol and methanol. 2 separate molecules, because my linear ester got cleaved into 2 new carbon chains. Cyclic ester gets cleaved into 1 diol chain. Very cool. All right, now we can't do the other synthesis on the bottom right because this is reactions with alcohols, and we'll need to still review those. I think I want to get us started by looking at previously seen reactions with alcohols. So we're going to start with this sec-butyl alcohol in the middle. And we're going to look at a few of the reactions we can do with it. I don't think we'll get through all of these before we have to leave. Do we have to leave? Really, some days I could just stay here all night. Like, I'm not sure when I would get tired.
That's what you say, and then in like 20 minutes you're gonna crash.
I did wake up at 5 a.m. this morning.
So I'm right.
We got 3 feet of snow yesterday, so of course I wanted to go skiing. But we didn't go. No, we didn't get out. And like, honestly, I was worried about an avalanche coming down and like locking us in the canyon. And also by 6 a.m., there was a line probably a quarter mile long just to get into the canyon. And by 10 a.m., that is like 2 miles long. So it was going to be a packed day because it got 3 feet of snow, but no, I couldn't do it. So I just got up and did work instead. Anyways, what have we seen that we can do with alcohols previously? Well, we've seen the halo ether addition. We even talked about it today. If I have an alkene and a halogen and an alcohol, alcohol is a precursor to an ether. So I can make an ether by doing halo ether addition. I do want to point out that carbon chain, the original sec-butyl chain, it looks a little bit different up there. 1, 2, 3, 4. It's in a zig-zig conformation. It's making a U rather than my zigzag conformation that I had before. What else did we see that we could do with alcohols back in OChem 1? Back early in the semester too. We saw that we could do SN1. I can take an alcohol and I can react it with HBr and I can make an alkyl halide. I could also use PBr3 to do this, or similarly, I could use SOCl2 to make the chlorine derivative. So those are all ways that I can do substitution on my alcohol. We saw that we could use tosyl chloride, and I can turn my alcohol into a tosylate group, turn it into a pseudohalide. And then lastly, we saw that we could react these with alkyl halides. And I can make ethers out of my alkyl halide. In fact, a way that would be more common to show this would be TBU. SN1, that's what that is. Okay, I know I'm kind of sucked up the rest of my time, but the last one I want to show, the last review here is dehydration. I can start with an alcohol, and I can make a halo ether. I can make an alkyl halide. I can make a tosylate. I can make an ether. I can make an alkene. Alcohols are great starting materials for a lot of different functional groups. Great diversity there. Okay, we're going to learn a new name for an old reaction, and then we're going to learn some new things that we can do with oxidation, the reverse of reduction. So we saw how we can come from carbonyls to alcohols. Next week, we'll see how we can go from alcohols to carbonyls. Get started on your homework this weekend. And next week, we'll do a lot of synthesis as we prepare for our Unit 3 test and the midterm after it. Okay. Take care, guys. Have a good weekend.